Welcome. Hi, I'm Ram. I'm part of the marketplace platforms at Uber.
Hi, I'm Nanda. I too work in marketplace platforms at Uber.
Here's our agenda today. We'll start with an overview of Uber Scale and some of the key challenges we were looking to solve. We'll then look at what it took us to evaluate Cloud Spanner and the systems we had to build to enable our platform on Spanner. We'll then deep dive into some technical learnings and what we plan to do next. Let's look at what scale means at Uber. Uber started back in 2010, and our systems have constantly needed to scale as business has evolved. As an engineer, one of the fun things at Uber is the opportunity to build systems at scale. Here are some of the numbers based on Q1, which essentially highlights what's the scale of our operations. We did close to 18 million rides, which includes trips and deliveries, each day on the Uber platform. We had close to 5 million active drivers and delivery people and have close to 103 million monthly active platform consumers. Uber is a global company with a presence in 10,000 cities and 69 countries across 6 continents. From the Eats side, we have 400,000 restaurant partners operating globally in 45 countries. A scale like this creates a unique set of technical challenges. The marketplace platform team is responsible for the fulfillment platform, which facilitates the core transportation flows for rides and eats. We are a huge into microservices. We have a robust infrastructure running on thousands of nodes across hundreds of microservices, and the complexity in running so many services increases as we scale. Let's look at a simple example of an offer acceptance flow. To your left, we can see a snapshot of the offer screen presented to a driver for a ride trip. The driver has an option to accept or decline, and from the driver's point of view, it's just tap of a button. But a lot of things happen in the backend. These drivers and riders are modeled as entities in our system, and when state changes occur, all these entities needs to be updated transactionally. As an example, once the driver accepts the offer, the rider also needs to be associated with that driver, and all the downstream systems needs to be updated and kept in sync. Also, the presented offer needs to auto expire if no action has been taken after a few seconds, and the feedback for this also needs to be propagated to downstream systems. These entities are modeled as state machines as it undergoes various entity state transitions from start to finish of a trip. Now, this is a very simple example of a two sided marketplace involving a driver and a rider. The complexity increases with Eats, which is a three sided marketplace involving a restaurant, a delivery person, and an eater. Also, with some advanced use cases like trying to batch more trips together for products like Uber Pool and Eats deliveries. The fulfillment platform handles all these real time use cases. So, more than a year back, we took a holistic look at our architecture with an aim to simplify and modernize them. Let's look at how we approached. We categorized our challenges into the following dimensions. One was focused on platform efficiency, and the other on data management. On platform efficiency, a lot of product teams across Uber use the fulfillment platform to build business features. We have to ensure that we build extensible components across all our product lines without introducing complexity. At the same time, we want to make sure we maximize on our infrastructure efficiency by improving throughput per core. Given the scale of Uber, even an incremental improvement here can have a meaningful impact on the overall infrastructure spend. From data management point of view, our current application architecture relies on an eventually consistent model and adds complexity at the application layer to deal with consistency. Also, when you have so many microservices, state management across all of them is a huge challenge. For our systems to be reliable, we need a strongly consistent and an available database that can scale to our needs and can also support complex transactions at scale. To overcome these constraints, We use solutions at application level, like maintaining transaction queues, sticky sharding, along with leveraging ring pop for coordination, and some patterns around transaction orchestration. But if you think about it, these application level complexity can be simplified with pushing some of them to the database level. So we classified our database requirements further into system and usability aspects. From systems requirement, we wanted an ACID compliant system which can give us 5 nines of availability and comes with globally consistent guarantees. Uber has multiple data centers, so the solution should work across data centers and should satisfy our latency SLAs. From a usability standpoint, we wanted support for relational modeling. Based on the previous example, we wanted support for a multifaceted marketplace where business entities are highly relational. It should have good observability for tracking and tracing issues and should be easy to scale as the business grows. So, with these requirements, which are super high level in mind, the team looked at different database solutions. We chose Cloud Spanner for evaluation as it satisfied all our core requirements. As we started ideating our solution on top of Spanner, we went through a process of identifying the gaps of what we needed to build before we could start using Spanner. Here are some of the things which we built specific to our use case. Our programming model is highly asynchronous, and we wanted all our Spanner RPCs to be asynchronous too. For this, we built an async Spanner client so that it can fit into our execution model. A background task execution system. We built an event sourcing solution on top of Spanner, which we will look into greater detail further down. TTL. As part of a real time platform, we needed support for TTL. So once a trip ends or an order is fulfilled, the data gets handled by a post trip processing platform. TTL support is needed so the data can be cleaned up once it's no longer needed by the real time platform. A transaction execution framework. We've optimized on different strategies for executing our transactions and also built tooling around detecting lock contentions and deadlock. Lastly, for monitoring, since all our metrics are persisted in our internal systems, some of which are also open source like N3 and Jaeger, we wanted Spanner server side metrics also to be available internally and closely integrated with our monitoring and alerting systems. Let's look at some of them more closely. We started off with a very lightweight Spanner client generated using Google's open source API generator and built on top of gRPC. This is a Java client, and as mentioned previously, this aligns closely and well with our async programming pattern and also gives us a better handle for tuning client side resources. We added more functionality to the client as part of session and transaction management. To give some more context, a session acts as a communication channel, and you can only run one transaction at a time on a session. They are reusable resources, so we built session pooling from ground up, which can auto scale based on usage. For transactions, we built different transaction execution strategies to reduce our transaction time. More on this later with an example. On observability front, we wanted to integrate it closely with our internal observability platforms like logging, metrics, and tracing. To talk more on other systems and solutions we built, I will hand over to Nanda, who will take it from here.
Thanks, Ram. To give you some context, we wanted a system for executing background async tasks with at least one guarantee. We were looking for an event sourcing solution on top of Spanner. Such a solution would be used for things like publishing internal state change events or to kick off post trip processing like sending customer notifications for things like ratings, etc. These tasks would be registered as part of the same transaction as other entities. For example, if the driver has ended the trip, the task to do post trip processing would also be registered as part of the same end trip transaction. Moreover, these tasks also needed to have a timer property where they can be scheduled to execute at some time in future, or they can be scheduled to execute tasks periodically. To build such a system, we introduced a task table where we can store all the registered tasks. We then built an efficient scanner, also known as tailors, that scans through this table and schedules them in memory for execution. They were named as tailors inspired by the Unix terminology, as the scans only look for new data. We were able to horizontally scale the system by having multiple tailors across different shards so that each scan got its own key space. This approach allowed us to detect any new tasks for background execution within milliseconds of them being registered. Another system that we built was a spanner monitoring service, which is a standalone monitoring service that imports critical stack driver metrics into our internal monitoring stack. The reason why we built this was to have spanner monitoring well integrated with our internal systems, especially paging and metric analysis. Some of the analysis that we were able to perform were session analysis, that is, to check if sessions are properly reused and for how long. Then transaction analysis, to analyze long running transactions. That is, Spanner provides interesting stats which allows us to introspect and dive deeper into queries and DMLs taking longer time. We get this data from Spanner and index it internally, making it easier to search and analyze. Building a spanner monitoring service allowed us to build an autoscaler functionality recently, to scale spanner nodes in an elastic way based on various server-side parameters like spanner CPU utilization and storage. While building these systems and testing spanner at scale, we came across some learnings that we would like to share that helped us along the way. Let's dive deeper technically. The first thing is request patterns. So it's important to have good understanding of request patterns in order to come up with the right schema. It is also equally important to understand how Spanner performs reads and writes for such a pattern. For us, we had three types of patterns: simple CRUD like operations on a given row. For such cases, completely random primary key like UUID works really great. It gives us the best possible distribution and also avoids hotspots. For multi-row updates or for accessing related items, use interleaved tables. It gives locality with parent rows, ensuring your joins are efficient. The other use case, as mentioned before, was to build an efficient scanner that scans through new rows. Frequent row deletions in your table can cause tombstones, which can make your scans inefficient, causing higher scan latencies. For such use cases, a combination of shard ID and spanner timestamp works really well. The problem with timestamps in a key, either primary or secondary, is that it can cause hotspots. Using shard ID prevents the hotspots and at the same time allows multiple workers to scan individual shards in parallel. There were quite a few learnings for us with respect to how we do transactions on Spanner. So, the first one was to optimize for reducing read write transaction time. Read write transaction time is measured as the time between the first operation in a transaction to the final operation, which is often the commit. In general, increase in read write transaction time is equal to increase in lock contention and consequently increase in abort rate in the system. When we started out, we had a lot of aborted transactions because of lock contentions. To have deeper understanding, we built a transaction analyzer tool to identify overlapping transactions and dig deeper into each contention, whether it is systemic or whether it's because of poor request pattern, etc. This allowed us to identify the type of transactions that can be retried on abort and the ones that should not. This was important as the last thing you want is all contending transactions retrying forever, causing more churn and contentions. For read only transactions, use snapshot reads wherever possible to increase your read performance. This allows the reads to be served from any replicas and consequently reduce the load on the leader. Let's look at an optimization story with respect to transaction execution. In the first graph, you can see we started off with a basic read modified write example where we read, then write, and finally commit. In all, there were three round trips to Spanner, not including the initial begin transaction, as we have a pool of transactions ready to go. Over time, our flows got more complex, where we often had to do multiple reads and writes within a transaction, thus increasing the number of round trips to Spanner. Now, why does round trip to Spanner matter? Depending on where your data center is, each spanner round trip is additional network latency. For example, if a transaction has 5 round trips, and if network latency is 30 milliseconds, you have lost 150 milliseconds just to the network. As we highlighted earlier, keeping a transaction open for longer also increases the chances of contention. So, to solve for this, we systematically broke down the transaction by identifying the parts of transaction that can happen in parallel by building a transaction graph. This allowed us to issue reads in parallel, but writes were still serialized as the DMLs needed to be in sequence. As illustrated in graph 3, this allowed us to reduce the round trips to spanner by just parallelizing reads. To solve for writes, we batched all writes and commit together in a single RPC using the mutations API as provided by Spanner. To look at other learnings with respect to Spanner client side and server side tunings, I will hand it over to Ram.
Thanks, Nanda. So here are some of the considerations for client-side performance and tuning. We'll look at two main aspects to tune on the client side: sessions and gRPC. We spoke about sessions and session pool. As part of session pool configurations, we recommend to maintain or always maintain necessary ratio of read-write sessions versus sessions that are used only for reads. A read-write session is a session associated with a transaction using the begin transaction API. You can size your session pool based on the expected workload and transaction rate. Also, session management APIs like create sessions and batch create sessions have high latency, so it's better to pre provision sessions instead of incurring cost during transaction operations. On the gRPC front, we always need to ensure to set appropriate deadlines to the gRPC context. We also learned that commit should be given more time to finish compared to other operations. For flow control, gRPC streams are bidirectional streams and are mapped to HTTP2 streams. Payloads are serialized as byte streams, which are then fragmented into HTTP2 frames. gRPC uses flow control mechanism in HTTP2, and this also helps in finer grained control for buffering in-flight messages. We optimized our flow control window depending on our payload size, which we found during our tests. Compression. This needs to be carefully chosen based on the payload size. We found our proto payloads are highly compressible, leading to bandwidth savings. Currently, only gzip is supported as part of the gRPC compression codec. We recommend on leveraging gRPC interceptors for observability. This can be plugged into the client for introspection and tracing. From a server-side tuning point of view, based on our testing, we could scale Spanner horizontally. One of the core metric for scaling Spanner nodes is CPU usage. It's recommended to operate below 75% on a smooth CPU usage. Spanner operational management is simple and it's easy to provision more nodes as and when you need it. It's also important to choose appropriate regions as Spanner offers variety of options like NAM3, NAM6, and regional Spanner instances. On the network side, since we run our infrastructure in our own data center, it's important to have an optimized routing strategy to Spanner server. We worked with GCP to make this happen. On the database workload, Spanner performs database splits and compactions based on traffic. This can be a load or a size based split, which might have a brief impact on latency. It's important to have an appropriate ramp up strategy so that there is minimal disruptions during the split. With all these learnings and optimizations, and along with the support of the systems we built, we performed simulations on Spanner with a synthetic Uber scale load. Before we look at these numbers, it's important to understand these are strictly dependent on data modeling and how transactions are run. This is highly use case specific and might not apply to every use case. Here are the following highlights. We are able to scale spanner nodes horizontally to more than 600 nodes with a 330,000 per second reads per second and 130,000 writes per second. CPU usage stayed close to 67%. And in terms of latency, we mainly cared about the following RPCs: execute SQL, execute batch DML, and commit latency, which were within our acceptable latency requirements. We were also working on a bunch of more optimizations to better the performance. So what are we doing next? We're looking towards building out new features like forecasting of spanner nodes based on predicted load and optimize on CPU usage. We're also looking forward to testing few spanner features like backup and restore. We'll also look at open sourcing some of our work in the future. Lastly, as we are working on productionizing our platform on Cloud Spanner, there's a whole team behind this, and lots of people are involved both on Uber and from Google Cloud team. As we embark on this journey, we are looking forward to this continued collaboration and partnership. On behalf of Nanda, I thank you for watching the talk.